Welcome to this video on an introduction to charge. Some of the things that we already know about charge I've listed over here just for your reference, but in this video we're going to be mainly focusing on the fact that charge is quantized. Now we want to keep in mind that we have two kinds of charge, positive and negative, and that like charges repel one another and opposite charges attract one another. We also want to keep in mind that charge is conserved, which we'll focus on in the next video, and that generally we define charge of an object as a deficiency or an excess of electrons. Some other major points are that charge is symbolized with the letter Q, which could be uppercase or lowercase q, usually interchangeable, although sometimes we'll want to use one over the other, and that the SI unit of charge is the coulomb, which is uppercase C. So let's jump right into this video's theme, which is that charge is quantized. So the idea of quantization is very important in moving ahead in science, both in chemistry and in physics. When you look at a bookshelf, we would say that the position of the book or of any book on the bookshelf is quantized, meaning that its position doesn't exist as a spectrum of different positions. There are discrete positions that the book can have. So the term discrete is an important term that we oftentimes will use when we're talking about quantization. So in other words, let's take this red book over here. This red book can only exist on these separate shelves. Now we have the opportunity or option to move it left to right on any given shelf, but we can't have the book hovering between two shelves, right? Or we can't put the book somewhere on a shelf, so to speak, between and below the shelf. It has to exist in just one of the places on the shelf. So this is the idea of quantization, that this is not a spectrum. So the idea of a spectrum of possible values is not one that we give to the idea of charge. And the reason being is that when we think about charges, they come in little quantities of electron charge. So the fact that this, for example, metal sphere is negatively charged is because I've drawn an excess of 6 electrons onto this. So we would say that the charge Q on the metal sphere is equal to however many multiples of the charge of each electron we have. And this is a mathematical expression that shows that charge is quantized. This, again, is an integer number, a whole number integer, and this is what we call the elementary charge, which is 1.6 times 10 to the negative 19th coulombs. Now, keep in mind that this is the charge of a proton and an electron, and so we must be able to put the negative or the positive sign out front in order to distinguish one kind of charge from the other. The last thing that we want to look at in terms of quantization of charge is that sometimes we're looking at a deficiency. So if this was drawn as the excess of charge, in other words, there are 6 extra electrons than there are protons. Over here in this substance, if I wanted to show a deficiency of electrons, one way that I might do that is, say, draw, in this case I'll just do 4 holes. One way that we think of this in terms of holes is that there are 4 electrons that are missing from a pairing with a proton. And so in this case, we can still use the idea of quantization. But now what we would say is that this is still an integer number. In this example, that would be 4. And the elementary charge is still 1.6 times 10 to the negative 19th. But now it's the charge of the excess protons, if you will, or the charge of the holes. So one thing that I will do often when I'm talking through some of these electrostatics problems is I will talk about having these extra electrons. I will only ever draw the extra ones. And then I will talk about having holes. If we think of this idea as holes or places for electrons to go that are a natural state, then we can understand more and more electrostatics, including the use of semiconductors later on down the line. In the next video, we're going to take a look at the idea of conservation of charge. So I'll leave you with a challenge. And the challenge is, if I had two charged spheres, and let's say this sphere had 60 electrons in excess, and this charge had 60 holes, or a deficiency of electrons. And I connected these two together by a conducting wire. What would the end result be after I let this sit for an extended amount of time? What would the charge be on each of the two spheres after they have been connected for a given amount of time? Go ahead and try that out, and then come back in the next video and we will figure it out together.